Okay, I'm getting into the last example here in section 3.4. Most of the time we've been talking about motion in a straight line. And, here at Flagler we have basically two types of students that need to take Calc 1, right? We have scientists and then we have economists. So I did want to do an example in economics just to show you that derivatives in economics are important. Probably some of you who have taken economics classes might even have calculated the derivative before without really knowing exactly what it is. But here's the deal. Okay, so in economics, in a very simplified form, we have two functions that we're interested in. C of x, which is the cost of producing x number of units of widgets, let's say. And then R of x is the revenue you would get from selling those units, the x number of widgets. Okay, so there's two derivatives that are interesting here. The marginal cost of production is the rate of change of cost with respect to the level of production. In other words, with a number of units. So it's dc dx. It's essentially the cost of producing one more item. Okay, the marginal cost. It's the instantaneous rate of change of cost. So it's the cost of producing just one more value of one more number of units. All right. The marginal revenue is the rate of change of revenue, or dr dx. In other words, it's the revenue you would get from producing one more unit. So, economists want to know, is the revenue I'm going to get from producing one more unit more than the cost I'm going to incur? So is dr dx more than dc dx? Because then I would want to know, well, don't do it because you're not going to make more money. It's actually going to cost you too much to do. So for example, suppose it costs this function. Say we happen to know that c of x is x cubed minus 6x squared plus 15x. It costs that number of dollars to produce x radiators when somewhere between 8 and 30 radiators are produced. So it stays that cost as long as I'm producing somewhere between 8 to 30 radiators. And that the revenue is x cubed minus 3x squared plus 12x. That's how much money I make from selling those x radiators. So let's say your shop currently produces 10 radiators, and we want to know about how much extra will it cost to produce one more radiator a day. In other words, what's the marginal cost, or dc dx, and what is your estimated increase in revenue for selling 11 radiators, for producing one more radiator and then selling all 11 of them. So the solution here, the cost of producing one more radiator a day when 10 are produced is about c prime of 10. So the cost of going up one more when I'm at 10. So c prime of x, you take the derivative of that. It's a very simple function, right? X cubed, derivative of that is 3x squared, minus 6x squared, derivative of that is minus 12x, derivative of 15x is 15. So c prime of 10, you plug in 10 for x, and you get 195. So essentially, the additional cost will be about $195 to produce one more radiator when I'm producing 10 already. Now the marginal revenue is r prime, dr dx. So revenue was x cubed minus 3x squared plus 12x. The derivative of that is 3x squared minus 6x plus 12, right? Hopefully we're getting comfortable with that. So the marginal revenue estimates the increase in revenue, the result from selling one additional unit. So what is r prime of 10? In other words, the amount of revenue about I would get when I'm producing 10 to produce one more. So the amount of revenue I would get, the additional amount of revenue I get, you plug in 10 to r prime, and you get $252. So if you increase sales to 11 radiators a day, you would increase your profit or your revenue by $252. Your cost, the additional cost was only $195. So you might, if you're able to produce that additional radiator, say, let's do it because I'm going to make money off of that.